Hello and welcome back to this course that is offered online. And today we are going to jump into this concept of neural computing missions. So before we go into this topic, we already know certain aspects of this. For example, you know what is the simple math behind coming up with a linear classifier in which we try to understand the relationship between the output error of a linear classifier and adjustable slope parameters that we discussed in the last class. So that is the same as knowing how much to adjust the slope and remove the output error, if you recall. In the same time, a problem with doing these adjustment is seems to be very naive. Is the model to update the best match is essential. We are trying to do that, and if you want to update it to the best match, we have to train the system, or we saw certain training examples in the previous lectures. And during this training process, you know what are the things that you are going to discard. For example, if the error rate is more, then we are going to discard that values, and we are trying to stick on to the value that has less error and try to reduce the error as much as possible. And a good way to fix this is to moderate the updates with a learning rate. So no single training examples totally dominate the learning. Again, a training example for real world can be quite tough. When I say tough, it's like noisy or contains a lot of errors. Sometimes it's very hard to comprehend what that error is. So moderating update in this way helpfully limits the impact of some of the false examples. So that's why sometimes the classifiers, which we saw earlier, is not enough. So we need to go beyond a simple predictor. As we saw before, we saw a simple predictor. We have to go beyond the simple predictor or a simple classifier. So we have to go for a key design feature of neural networks that actually comes from understanding certain limits that these predictors and classifier has. In order to understand what is the limitation of these kind of predictors and classifiers that we have seen so far, let's start with a simple Boolean logic. Consider here, maybe you are already familiar with certain Boolean logics. Whenever we have certain input, and with those inputs you are trying to find its equivalent output. For example, let's consider input system in which you have like two inputs. Let's say A and B are the two inputs, and you have an AND gate and an OR gate. Let's try to check for the truth table of this system. Well, you already are familiar with the system, like for 0 and 0, and is 0, or is also 0 output. 0 1, you have 0 and 1, 1 0, 0 1, 1 1, 1 1. So this is very basic gate that we have here, and with this basic gate we can try to understand or try to imagine a simple linear classifier. If you recall, it can learn from training data whether the data are governed by Boolean logics function or not. So it's natural to useful for anyone to start with certain links or correlation between certain observation. For example, we talk here about AND gate, right? So AND can be like there is a correlation between, say, rain and malaria. There is a correlation between these two. Or you can consider when you have rain and if the weather is more than 35 degrees, Is there more malaria? Or of these conditions, which is true, like you are already talking about two logics. One is AND logics, the other one is OR logic. You can consider other things like when you talk about other epidemics or other features, you can also think about is there any correlation when two things exist, your possibility of having the third thing, that is nothing but the AND logic, right? In the same fashion, you can also think about the OR logic. If this or that, if any one of this is present, any of these two is present, then you can conclude that the output is true. So to understand this example, you can consider for AND logic we can think about this simple mechanism in which, let me put it this way, suppose you have your points, suppose each points represent certain values. Let's say this represents 0, 0, this one represents 0, 1, 1, 0, 1, 1, and I'm calling this as an AND gate, say AND gate classifier. And let's also have another one, OR gate classifier. Let's try to put the same thing here again. Okay, let me put it this way here. Zero, 1, 1, 0, 1, 1. Okay, given these conditions, is it easy for you to have a classifier that can classify the input and the output, like what is the place or where you are going to have the dividing line in this case? In fact, there are many variations of dividing lines we can think about that would work for simple problems. And if we talk about the linear classifier, where we have the y equals ax plus b, so to learn the Boolean function AND, you can have the actual dividing line over here, right? This actually divides both the true values or the output whenever the output is 1 and whenever the output is 0. In other words, you can see it's simple classifier, Boolean classifier, right? 0 and 1 classifier, the output based on the output. You can have a very simple system. On the other hand, if you have this OR logic, this time only we have 0, 0 as the output is 0. The other three you have output as 1. So you can have a simple classifier over here, right, that can classify both input and output. So with this thought in mind, let's check about what happens when you have a different logics. These are very simple logics. In fact, they are basic logics that we have. Let's talk about one more gate. It's called the XOR gate. And we know that XOR, when your input is like say A and B is given, and what is your XOR output? XOR is exclusive OR, and you know when you have 0 and 0, the output is 0. When you have 0 and 1, the output is 1. And when you have 1 and 0, again the output is 1. When you have 0, let's put it as 1 comma 1, the output is 0. So for this, how are we going to have a same simple linear classifier? If you just think about again the same line that we have, let's talk about the points in the line. Where are we going to put the classifier? You can't just divide in one place, right? For example, if you put it here, if suppose your dividing line is over here, it doesn't really classify according to the XOR logics. So XOR function is pretty different from the normal functions, so which means that this is one of the major limitations of a very simple linear classifier. So a simple linear classifier is not useful for this kind of problems where a simple straight line cannot classify the system. So that's why we want a neural network to be useful for many of such tasks where the underlying problem is not a linear separable system. Or in other words, you cannot have a simple linear classifier like just a straight line to classify or divide. So if you want to fix this kind of problems, maybe you may have to go for different suggestions here. How about here? Yes, your actual dividing lines, you have two lines right now, and this is one of the simple ways in which you can have a solution for this. And it's kind of a multi-layer or multilinear classifier. You can divide up the data that cannot be separated by a single linear classifier. You can have multiple linear classifier to achieve this task. So we divide into building, we can do the same thing by dividing a system. Actually, as I told you, this is the one which are going to give us in a direction of neural networks. So as I told you, we can use the multiple classifier together, multiple linear classifiers together to achieve this task. So that's the basic idea behind the neural networks. So you can imagine that there are many linear lines can start to separate off even unusual shapes of regions of a classification. That's why neural networks are quite strong in classification, and they achieved tremendous accuracy, especially when it comes to image and video related classification problems. So before we divide into building a neural networks made up of many classifiers working together, we have to understand what is the actual neural network is, and we want to get to know about what are some of the basics behind the system. Let's talk about some basics of neural networks, which are very important aspect of the entire scheme. Okay, let's go here. Okay, so what we see here is nothing but a very simple neuron, and as you can see here from this neuron, the neuron shows the myelin sheet, dendrites, nerve cell body, and axon. Well, this is a biological neuron. So what we are going to discuss, or what we are interested in, is something called the artificial neural network, ANN, artificial neural networks. So it is in fact vaguely related to this biological neural networks. So this is actually what happens here is that as you can see, x1, x2, x3 till xn, they are the inputs, and this input is given or taken into the cell body via dendrites. So as you can see, the dendrites are here. So all these are dendrites, and from the dendrites you are actually taking in the actual system. So this whole structure is called the neuron. In other words, they are in fact give us the basic understanding of a cell body in a system. So when you have all the inputs like x1, x2, x3 are taken as the input, they are kind of combined together and sent into this nucleus. And that's where in our artificial neural networks a simple process happens. Actually, when you implement ANN, it's like a signal connections. Actually, signals are given as the input, and you're expecting an output over here like y1, y2, y3. There are several things at the output, and they are connected via the myelin sheet, and this output is given as an input to the next system. So this is the very basic information if you want to check, and this is inspired from the human brains. So basically, though the neurons although have many different forms, all transmits an electric signal from one end to another end. That's the basic idea. So as I told you, from dendrites along the axon, from dendrites in this input, and it is taken to the axon as the terminal node. So these signals are then passed from one neuron to another neuron that are connected to this other end by another dendrites of the set of dendrites from other node. So that's a very simple thing that happens in our body whenever we sense a signal, maybe a light signal, a sound signal, or even a pressure signal, so on. All these signals are in fact are kind of transmitted by means of certain electrical signal, and our neural or nervous system in fact does the whole process of sending the signal from one neuron to another neuron. And one interesting fact is that we are capable, or in other words, very capable human brains have around 100 billion neurons. There's just only one neuron we talk about here, but our human brain has 100 billions of neurons. If we talk about a fruit fly, a very small creature, it's a fruit fly that gets into the fruit and lays the egg inside the fruit. So when the egg hatches, the fruit fly, the baby fruit fly, you can say, it eats up the egg and it grows up, eats up the fruit and it grows up. Eventually the fruit gets spoiled actually, if you are cultivating some fruits in the farm. Anyway, the fruit fly has about 100,000 neurons, and they are capable of flying, right? That fruit fly is capable of flying. They are capable of feeding themselves, or capable of evading dangers, finding food, and many more complex tasks. They have only 100,000 neurons, but they perform many tasks. A simple fruit fly. So this number of 100,000 is quite easy for current technology to build a modern computer with 100,000 neurons, but it's very hard to replicate the same functionality of a fruit fly. That's quite hard for humans to do it. And we talk about certain worms, like we know small worms, and they have some worms like they have just like around 300 neurons, and they do certain tasks as well. Anyway, I just want to give some information about how strong the actual design of the nature is. As we can see, there is a tremendous activities that is going on, and we humans find it hard to just imitate them. Well, we are trying to use this so-called artificial neural networks just to help us in computing simple tasks. So we are going to consider how this is going to work. In fact, we are going to see how the whole process of this biological neural system has been mapped into the artificial neural network and how it is being done. Simply what happens is that we have a linear function of the input, then its output does not take any forms, special forms, rather it just has the constant. You are going to multiply with the input, and with certain uh, functions we are going to analyze the whole process. So in the lecture we are going to see how the whole process is going to happen. So observation suggests that the neurons don't react readily, generally speaking, but instead suppress the input until it grows so large that it triggers an output. So the neurons, I repeat, the neurons don't act right away. It gets the input, it does not act right away. Instead, it suppresses, or in other words, it suppresses the input until it grows so large that it triggers an output. So you can think of it as the threshold that must be reached before an output is given. So there should be a threshold we have to reach before an output is fired. So you can think of this the whole process with respect to threshold. The threshold should be achieved or reached before the output is produced. So in other words, you can think about various other examples. Before reaching certain things, you cannot do certain things. That is very simple examples. Maybe, for example, you are driving a car and you get the fuel tank seems to be going to empty. So you feel that is a threshold. Once it's go to the yellow sign, then you're going to fill in the tank. So that's a triggering process for your action, right? So likewise, you can think about anything, like even you get hungry, then you're going to eat. So that hunger, that is the threshold that triggers this hunger, right? You don't eat if you skip a meal, then eventually you're going to get hunger. So likewise, there are many other things you can think about, how one thing initiates the other output. So until a certain threshold is reached, you're not going to get the output. So this is one of the simple concept that we have to understand in whole process. So a function that keeps the input signal and generates the output signal, but takes into account some kind of threshold. We can say that is called the activation function. We will understand what is this activation function as we move forward into this lecture. There are many such activation functions in this system. I will talk about a few of those activation function very short in terms of getting some idea about what is this activation function. So there is something called a step activation function. It's called the step, or in other words, it's a step function. So as you can see here, when the input is low, the output is 0, right? It just stays at the 0 level. But once it reaches certain threshold in its input, a certain threshold is reached, so we are reaching a certain threshold of its input, then it's actually triggering. In other words, this artificial neuron behaves just like a biological neuron, where the biological neuron also triggers or sends the signal. So since this kind of triggers, or we call fires, we often use the term like neuron fires when the input reaches a certain threshold. So these are some of the terminologies. I will also cover up some more terminologies as we move forward. So we can improve this kind of step function. You can see the step function is happening, but in reality step functions are not occurring in nature. For example, because this is so sharp, right? You have an input and suddenly at one point you have a sharp increase. Basically in the nature, we have a very smooth increase. We always have analog signals, right? We don't have any digital signals like this. This step function is kind of a discrete function. Let's talk about another function here. This function is called the sigmoid function. Sigmoid function. So as you can see here, nature rarely has the very hard and sharp edges, for just like in step function, but this kind of smooth function is mostly is possible to have in the nature. It's also very similar things that people feel that in artificial intelligence researchers, most of them also feel that this kind of simple and smooth functions then can accompany many of the naturally occurring uh, objects. So at times these sigmoid functions are called as logistic function, and if you recall the logistic functions, you might remember about the logistic regression as well. So anyway, we'll stick on to logistic function first, and this logistic function itself has a term like y equals 1 by 1 plus e power minus x. Okay, let me redraw that. Okay, so it's very simple mathematical term, and here e represents the constant. The mathematical constant of e is 2.71. Oops. It goes on and on and on. Okay, so that's the value. Anyway, we'll talk about this kind of functions once you go into that area, but generally speaking, you can actually set up and see what are the values. If you put x as 0, for example, anything power 0 is 1, right? Anything power 0, even if it is e power minus this one actually becomes 1 by 1, right? So you can think about in fact 1 by 1 plus 1, so that's equal to 1 by 2. So that's a simple process. It's kind of a half the value you get. Y equals 1 by 2 when x is 0. So that's a simple and powerful reason for choosing a sigmoid function over many other functions. For whenever you have certain inputs, you can always expect a certain output in a more reasonably smooth, the so-called S. It's kind of a S-fashioned function. Okay, so let's talk more about this actual system. We talked about what is a biological neural system, and we are trying to relate this with the so-called artificial neural network. So okay, what is happening in the actual system? What we are doing is that we are taking the inputs. Initially we talked about x1, x2, x3 till xn, right? And these are the inputs that are taken from the dendrites. So now we are actually having a map or model that has been taken from the biological system, and we are actually putting up here as an ANN system. So here you have all the inputs coming in, and this input is combined together. What we are doing here, summation. You can see summation of Wi and xi, right? You are summing up everything together and put this resultant value as the input to the sigmoid function that controls the actual output. So you have the summation is done here, right? The summation, and then after that you have a certain function f, a certain function. Maybe you can have a sigmoid function. Later on we'll see there are a few more functions which you can use as well. So sigmoid function, so sigmoid, you can say sigmoid threshold, because as far as sigmoid or any function is concerned, just we saw a step function, for example, after a certain threshold it jumps up to 1, right? It goes, shoots up. Likewise, as we have the input reaches a certain value in sigmoid, again it goes to the upper. In other words, it goes up, reaches to a certain point. So it all depends upon the threshold. That's why we still keep that name threshold here to understand what it is. And after that, this is taken as the output. So this simply reflects the real neural or real neuron thing. So this diagram, this idea of combining input and then applying the threshold with the combined sum is being illustrated in this simple figure. So if you combine, the signal is not large enough, as I told you before, if the combined signal is not large enough, then the effect of sigmoid function is to suppress the output signal. If the sum of x is large enough, then the effect of the sigmoid is to fire the neuron. It will fire the neuron. And if only one of the several input is large, the rest is small. Just imagine that only one input is large and the rest of the input is small. So this may be enough to fire a neuron, right, generally speaking. And what's more, that neuron can fire if some of the inputs are individually almost but not quite large enough. Then because being combined, the signal is large enough to overcome the threshold. We will analyze certain features of such system, and we'll see how it can be viewed, generally speaking. So we'll talk about few more issues before we jump into the actual working process. Okay, So now I just want to discuss about a few points with respect to the hyper parameters, so-called hyper parameters, and they are nothing but the learning rate, cost function, back propagation, and then learning paradigm. So what are these hyper parameters? They are actually simple constant parameters whose values are set to be for learning process. So this whole thing about the parameters, for example, hyperparameters includes the learning rate, one of the main point of hyperparameter, and the number of hidden layers and batch size. These are also the hyperparameter. We'll talk about the hidden layers later on. Just for the time being, understand hyperparameters. They include the learning rate, number of hidden layers, and batch size. So you might wonder what is learning rate, or what is hidden layer, what is the batch size. I'm going to talk about this soon. Now we'll talk about what is learning and what is learning rate. Okay, so when it comes to learning itself, learning is an adaptation of the network to better handle a task by considering simple observation. So in the example that we've seen earlier about a simple predictor and a classifier, you might have noticed we had training, right? Training part. That training part is actually a learning part. If you analyze, we come to know about the output, and then we come to know that the output that you have is deviating from the real value, so you try to reduce the output, right? Again, and when you reduce the output, you find that the output is closer to the expected value, and still you are trying to refine. So this whole process is happening. So that's why the learning is an adaptation of a network to better handle a task by considering simple observations, and this learning includes the adjusting the weights. So here again, this WI, I haven't talked about it much yet. We have this WI, right? So this WI is actually weight. We have to include the weight for all the values that we have, all the inputs that we have here. And this is a very important thing that we have to understand, that learning involves by adjusting the weight and the output, or in other words, adjusting the weight, because the weight adjustment is based on expected output of the network. And if you change the weight, in fact changing the weight improves the accuracy of your system. That's the main goal. So this is done by observing the errors. You observe the error. If the error is too much, change the weights accordingly so that the error can be reduced. It's a very simple way and very similar way in which we saw earlier how we come to know about an error, and based on the error you are going to adjust a value, right? Same way here we are going to adjust the weight. That is a very important process of the whole learning process. Okay, so again I want to repeat this one more time, that actual learning process is done by minimizing the observed or observation error, and learning is complete when examine additional observation does not useful to reduce the error. So after learning, the error rate typically does not reach 0. Of course we want the error rate to be 0, that's going to be good and perfect, but in most cases it does not reaches 0. If after learning the rate is too high, the network typically has to be redesigned. Understand? If suppose you have your system and you feel the error rate is going up and up, it's not reducing, then which means that you may have to redesign your entire architecture. So that's one of the typical system that we have to understand. So what we do is that by defining a cost function, this is evaluated periodically during the learning process. So that's where the cost function comes in. You have to understand what is the cost function, or in other words the loss function. So that's one of the other things that we are going to see about it eventually. So we know that if you want to understand or redesign the entire system, if the error is too high, you're going to redesign the entire system. And if you want to understand what is actually happening about the error, it is better for us to look into a better cost function that evaluate the learning process periodically. You're going to check. As long as its output continues to decline, the learning continues. If the error is trying to reduce, if you are reducing the error as for every iterations, then you are going to continue the learning process. The cost is frequently defined as the statistics whose values be only approximated. Okay, let's talk about the cost function itself. Even before talking about cost function, maybe it is good to understand what is the learning rate, right? So you have to understand what is the learning rate. We have the learning rate here. So learning rate, a learning rate defines the size of the corrective steps that the model takes to adjust for errors in each observation. Got it? So what it means to be learning rate? A learning rate defines the size of corrective steps the model takes to adjust for errors in each observation. A higher learning rate shortens the training time. That's very essential for us. But with lower learning rate, there are certain things that you have to observe when we talk about learning rate. For example, we have to consider the accuracy of a system, because we need a better accuracy. A lower learning rate takes longer, but with potential of greater accuracy. So we have to check for a better learning rate. As we move forward, some of these terminologies I will repeat, and then you will come to know what is a learning rate when we discuss about actual neuron design. Okay, coming to the cost function. Cost function is a function desirable for us to model. It's a simple probabilistic model actually, and we are going to consider what is a cost function when we talk about the actual learning process. And one more factor that we need to understand about cost function is that whenever the learning rate is high, we know that network has to be redesigned. So that's where the cost function can be very useful, because cost function can help us to evaluate the system, evaluate periodically during the training process. So as long as the output continues to decline, you can continue the learning. So cost functions can help us to do this evaluation process. And as I mentioned before, the cost functions or cost is frequently defined by means of certain probabilistics or statistical methods whose values you can simply approximate, and you can just usually get a certain number as the output when the error is low, and that's the process actually for looking for some correct answers that we are trying to estimate. Okay, then comes the back propagation. We will also talk about this back propagation in detail later on, but just now I want to give you some instructions about what is this back propagation. Generally speaking, back propagation is a method to adjust the connections or adjust the connecting weights to compensate for each error found during the training. So during this process, the error amount is or the errors that we get is kind of divided among the connections that has in the neurons, and we are going to actually back prop, in other words going back and trying to calculate the gradient, and based on that, in other words calculate the gradient, I means we are actually doing the derivatives of the cost function that are associated for the given state with respect to the weights. So you can see how the term weights, cost function are all related with respect to the back propagation. So the weight you have to update every time. So the weight updates can be done via certain the so-called gradient, stochastic gradient descent method, or other methods in case of the actual learning process. And there are certain ways we can actually analyze the entire process. There is a feed forward networks, the back propagation methods. So we will consider what is the back propagation with examples when we go to this section, right? And there are different types of learning paradigm, like we have supervised learning, we have unsupervised learning, we have the so-called recently we have this reinforcement learning. So these are some of the learning paradigm, and there are a lot of different types of networks are also available. Like we talk about the so-called artificial neural networks, and there are also so-called Bayesian networks, and there are still we have many non-parametric methods. Some methods are related to the so-called evolutionary computing system, and recently the so-called ANN, we have the so-called long short-term memories. Of course, there is another system we have in the deep learnings called recurrent neural networks, convolutional neural networks. These are some of the familiar things that you might come across. So anyway, after we consider what is an artificial neural networks, then we will jump into the other topics about so-called convolutional neural networks. I will discuss what is a convolutional neural networks, what is a recurrent neural networks, the CNN, RNN, and then LSTM, the long short-term memory. So these are some of the recent things that are going on with respect to this artificial neural networks. Okay, let's proceed with this as we move ahead with actual process. Now we are in this part of the entire system. So we have the so-called neurons. We talked about neurons, and then let's see here. Yeah, here's the simple connections that we have. So if you notice here, there are kind of three layers, like layer 1, layer 2, and layer 3, and each layer has 3 neurons, and you can see those connections. Each neuron is connected to the other neuron. For example, in layer 1, neuron 1, 2, 3 is connected to all the neurons in layer 2. So input is given to the input section, and output is taken from we can see it's taken from layer 3. So it's a simple way in which the neuron connections been replicated. Even in the biological system, the neurons are connected with each other. But remember that we are not exactly mapping the actual biological neural system into the artificial neural networks. It's kind of vaguely related though. Yes, so here you can think about something interesting. Okay, here you would be wondering like, okay, I have this neural networks and I have this connections and all those things is there, but what part of this architecture does the learning? We talk about learning, right? So what part of this architecture does the learning? And what do we adjust in response to the training example? What are we going to adjust? Is there a parameter that we can refine like slope in the linear classifier that we talked about it earlier? So these are some of the basic questions we have to understand. The first one, okay, look at the architecture. Where is the learning process? Second, what do we have to adjust in response to the training examples? Is there any parameters that we can refine, like the slope of a linear classifier that we talked about earlier? So when you look at this architecture, one thing is very clear. So that is something like you can see the strength of connections between the nodes. So within a node we can or we could adjust summation of the inputs. In other words, we can say that we could have adjusted the shape of the sigmoid threshold function. Anyway, we'll move forward slowly and I will take you step by step in getting this whole process. Okay, if we consider this one here, if a simple approach, if you look at here, as we can see the connections, and we have certain weights W11, W12, W21, W22, so on and so forth. So let me simply explain what it is. These are simple numbers that help us to understand. For example, the connections that you have here, say W12, what does it mean? It means that you have a connection between node 1 of layer 1 to node 2 of layer 2. So weight, you have W2, 3, right? Here is W2, 3, this part. It means that the weight associated with the signal that passes between node 2 in a layer to node 3 in the next layer. So in this case, node 2 of first layer to node 3 of next layer. That's what W sub 2, 3 simply means. So let's talk about in detail in understanding the actual process of how the connections can be illustrated with the simple observation. So anyway, right now you have understood what is what with respect to things. Let me just go back a little bit. So you have the inputs. After that, you are summing up all the inputs with certain weights, right? So the same thing here. You have inputs and you are combining this input with certain weights. And unfortunately here we have 3 layers. So I will describe what it is now, and later on we'll talk about a simple 2-layer network to understand things better. Okay, let's examine this further, how different types of connections can be made with all sorts of different ways. Okay, you can actually do one thing, like if you can see you're connecting node 1 of layer 1 to all nodes in layer 2, right? Likewise, your connection node 2 of layer 1 to all nodes in layer 2. So this a rule to connect to all nodes in the next layer? Well, just for sake of uniformity and organization, we are kind of connecting fully. It's kind of fully connected system, and it's quite easy for you to implement such system in real-time implementations. So, well, again, the layer 1 has only 3 neurons. In reality, of certain practical examples, you may have like several hundreds of neurons coming at the input certain cases, and you may have again many neurons in each layers. So in just make sure that there is certain clarity and there is no ambiguity. We want to make sure we don't want to miss certain weights or connections, because whenever you want to improve the rate in which the error has been reduced, sometimes if you miss certain connections, it will be very hard for us to manipulate, unless certain connections can be taken off based on the domain in which you are working on. Anyway, just I want to tell you about this information. So generally speaking, having less connections and more connections absolutely depends upon solving a specific task. So learning process will actually emphasize how certain connections are essential or they are not essential. But basically this is how we work, so that everything looks clear for us to start with. Okay. So there are few more stuff with regards to this actual process. The network learns to improve its output by linking or by refining the links that you have with respect to weights in the network. So that is one of the key part that you have to understand. So the network, let me put it in this way, network learns to improve, it learns to improve its output by refining the learning weights inside the network. So that's one of the key observations. So some weights become 0 or close to 0, and where some weights do have other values in the whole thing. So you can see how things can be analyzed. A 0 weight means the signal is multiplied by 0, which results in just 0. So in other words, whenever the weight is 0, it's kind of the link is kind of broken, right? So even that happens. So just for your information, I'm just following through how this thing is happening. Okay, let's get things more simple. Let's analyze the entire system by means of very simple network. Let's start with this 2 node in each layer with 2 layers. We understand the whole system, and then we can move on to a 3 layer system for us to understand. Okay, here it is. This system is a 2 layer example in which you have an input and output, and it is fully connected. Okay, let's consider you have your input is 1.0 here and here 0.5. Okay, So these are the inputs for the small neural networks. So here each node turns the sum of input into an output using an activation function, and we know that we are going to use the sigmoid function. We are going to use the sigmoid function, which is y equals 1 by 1 plus e power minus x. So x is nothing but the sum of incoming signal to neuron. What is x? X is nothing but the sum of incoming inputs into the neuron. And what is y? Y is the output. Got it? These are the x, say x1, x2, and here is y. Right? That is the output of the actual neuron. How about the weights? We talk about weights. If you recall, we had W1, W2, and so on and so forth, right? We'll simplify. I will simply examine. Let's see what it is in very short time. Very clearly we can understand what is what. Okay, how about the weights? So we are supposed to have weights here as well, right? So for example, in this case, we have only like 4 connections, right? And for 4 connections, you are just going to have 4 weights. For each node, you are going to have only 2 weights. Okay, let's try to write it out. Say 1 to 1, so W11 and W12, and this is W21, this is W22, right? And let's give some random values initially for these W's. Let's take W11 equals 0.9 and W12 is 0.2, W21 is 0.3, W22 is 0.8. That's 0.8. Okay. So with this values, we are going to see what is going to happen. Okay, now everything is in place. Now we can actually start the calculation from the first layer with the first node in the input. Let's begin the whole process as I told you. Come to the first layer here. The first layer, okay. So the first layer is in fact it is the input layer, and basically input layer does not do anything other than just take the input or just represents the input signal. So that is, in other words, the input nodes don't apply any activation function. So input is just given to it's taken by the nodes, but there is no activation is applied at the input layer. And maybe you can think about it. Is there any research directions on that aspect? Well, for the time being, let's move forward with what the actual neural network is. Okay, so the first layer, the input layer, as I told you, just it represents the input signal, which means that you're not going to mess up with it using certain activation function. Coming to the next layer, the second layer, in this case that is also the output layer. Okay, so the second layer, we do some calculations. So what do we do here? For each node, in this layer, the second layer, we need to work out certain combinations with the input. If you recall the sigmoid function that we have here, we can also use the sigmoid function as a whole process, because we are going to also look at the entire process with the output as well. So we know that the x in the sigmoid function is the combined input into a node. So in other words, you can consider like this: you have the input, you have the weight. So one more thing is, like when I say about input layer, in input layer itself, as we know, the input is 1 and 0.5. Right away nothing happens in the input layer. Even we are not going to do anything with the other process, other calculations. Anyway, what we have, for example, if you have inputs, say 3 inputs A, B, C, and we have 3 weights WA, WB, WC. So what we are doing is, like, you are going to sum up this combined input. The input and the weight is being combined together at the second layer we are talking about. It's combined together. You are going to multiply A with WA, B with WB, C with WC, and you are going to sum up the whole thing. And then you are also looking at this sigmoid threshold function. So again, we'll focus on actually what is happening with the layer 1, or let's say you can focus on layer 1, node 1, for example. Layer 1, node 1. Both nodes in the first layer are kind of connected to the next layer's node. So these input nodes have simple raw values of 1.0 and 0.5 as the input. The link from the first node has a weight of 0.9, and the link from the second node has the weight of 0.3, and this two combined, it goes into the input of the first node in layer 2. So what is actually happening, the whole process, again, for this 0.2 and 0.8 is going to this part, right? So what is happening in the whole thing? We can simply calculate what is happening with respect to this process. For the x, you want to calculate x. So x equals, I'm talking about this x equals, in our case, 0.1 times 0.0, .1 times 0.0 plus 0.5 times 0.3, right? So if you try to calculate, so x is 1.05. So if you don't moderate the signal, we would have very simple additions. Because of weight, actually we are moderating the signal by means of weight. We had only 0.1 and 0.5 as the input, and the weights, actually, as I mentioned before, they are the ones which does the learning process in neural networks, as they are iteratively refining the entire system for a better result. So now we have this x is 1.05. So this is actually combined moderated input in the first node. Remember, this is the combined moderated input in the first node, for the first node combined moderated input that we have. And let's see what is going to happen if you want to calculate the sigmoid function, which is we know y equals 1 by 1 plus e power minus x. So if you just use calculator, you can find the answer to this, which will be 1 y equals 1 by 1 plus that is e power minus 1.05, right? So maybe you will find some answer similar to this one. That's equal to 0.7408. Okay, that's the first information that we got here. That's the first information that we got here, right? So you can do the same thing for the other nodes as well. So we have the output right now. Right now this is the output you got, and you can also do the same thing for the other node. When I say other node, we talk about one side we already finished. We have to do the other side. Okay, let me do it here for the other side. X equals 1.0 times 0.2, right, which is nothing but here 0.2 plus 0.5 times 0.8. Okay, so again you can calculate what is y here. E power minus 0.6. What values you get? 1 by 1 plus 5488, and your value is 0.6457. Okay, so you got the y value to be this one. So you got those two values as the output, right? This is second output and this is your first output. So in other words, what you just did here is that we actually found the actual outputs here. Let's write it down. Here is 0.7408 and here is 0.6457. Well, that's great. You already got an output. So in fact this is a simple two layer, each layer has two nodes, and you can actually manually calculate what is the output. If you have say 4 layers, 8 layers, or even each layer has 100 nodes, maybe it's very hard for you to do it. But these days we do have many packages in many programming languages, including MATLAB or Python. They can help you to do the whole process very easily. You can just program it. It's easily for the computer to do the iterations several times or the calculations quite easily. Well, coming back to this problem here, so as we have just used the whole process of multiplying the input with the weights and adding them together, and this in fact is actually what we're doing here is that we are in fact doing the matrix multiplication. So just to recall the matrix multiplication, how it happens, like you go from row wise into the column wise. Like in this case, for example, 3 times 6 plus 4 times 8. You're doing that one part, so that is actually here. So this whole process is a simple matrix multiplication. So what we have here, the weights W1 1, W2 1 2, W2 1, W2 2, and you have the inputs, input 1, input 2. You are actually doing the same process of multiplying inputs with the weights. You're doing this process of multiplying the inputs with the weights, and that is nothing but it's a very simple matrix multiplication. So that's why this matrix multiplication is quite vital for us, the whole process for calculating the actual inner product of this whole system, and that can help us to moderate. We are actually moderating the input signal with respect to the weight, and this whole process can be analyzed for us with respect to matrix informations. So this is the general outline. We know nothing is happening in the input layer when there is only 2 layers, but at the output layer we are actually multiplying the input with the weights, and you are getting the output after checking for the threshold value, whether the threshold has reached or not. In this example we used sigmoid function. So basically this is the whole process. In fact, it is the matrix, general matrix calculation is happening. In other words, we can generally speak this as, or tell it as, x equals wi. The x matrix is the multiplication of w and I matrix. That's the whole process. So the multiplication is done, and this is very simple multiplication. Of course, we saw only 2 cross 2. When you have a bigger matrix, you may have a more complex system, and of course for implementing neural networks you may go for certain computing mechanism. So coming back to this activation function, where is the activation function, how it is employed, you might be wondering. So as far as as far as the activation function is concerned, so they don't need the matrix multiplication. So all we need to do is that apply the activation function or the sigmoid function to each individual elements of the matrix. You can do that. So in other words, you can simply make it like output sigmoid of x, right? So activation function simply applies the threshold, as we know that, and you're going to have a threshold and squeezes the response to be more like to the biological neuron, as we are already expecting that to happen. So for the final output of the second layer, you can have it like this. So this output matrix O equals the sigmoid of the x matrix, and we know that x is the multiplication of W and I matrix. So that's a lot of calculations. Yeah. So anyway, we simply saw that how a simple 2-layer network, two-layer neural networks with 2 nodes with a given input, we can get an output. So we saw a simple example how effectively we can do it in this example. And in the next lecture, we are going to see an example with 3-layer examples with the matrix multiplication where we are going to perform with another example. And after that examples with 3 layer, I will give you, or I will try to implement one simple method in Python, and you can see how it can be done and how it can be applied. So once you understand this concept of ANN, it is easier for you to switch into any other advanced system of neural networks. So I would like to stop here, and we will catch up in the next lecture.